This program is brought to you by Stanford University. Please visit us at stanford.edu.
Well, good evening, everybody. I'm glad to see you back, all of you. So nice to have such a large class. The last time we discussed the influence of electric and magnetic fields on charged particles. We know what they do. We know what electric and magnetic fields do on charged particles. They push them around, they pull them, they exert forces. In fact, we even wrote some equations. Let's write down the basic equation. The basic equation is that the force on a charged particle, F, is equal to the electric charge of the charged particle. Why is that there? That's there because if the charged particle wasn't charged, if it didn't have any charge, there would be no force on it. And then that gets multiplied by the electric field. Let's just call it the electric field. Plus something that depends on the magnetic field. And the thing that depends on the magnetic field is the cross product of the velocity with the magnetic field. That's the basic influence of electric and magnetic fields on charged particles, is to exert forces on them, to push them and pull them around and so forth. The missing piece thus far is what is it that determines the electric and magnetic fields in space? What is it that determines whether there's an electromagnetic wave? What is it that determines if an electric charge produces an electric field and so forth? What are the equations which govern the fields themselves? Those equations are called Maxwell's equations, and those are the equations we want to discuss this evening. They're the equations which tell you how charged particles affect fields. Here is the equation which says how fields affect charged particles. The other half of the coin is how charged particles affect fields. Why is it necessary that charged particles affect fields? Well, it's a kind of action and reaction thing. If electric and magnetic fields can influence particles, what does that mean? It means an electromagnetic wave can come, hit a charged particle, and send it off flying off in some other direction. It can add energy to the charged particle. Well, if an electric field can add energy to a charged particle, then it had better be that a charged particle can suck energy out of an electric field. Otherwise, energy wouldn't be conserved. So it stands to reason, it's a kind of action and reaction thing, that if electric and magnetic fields can do things to particles, charged particles, then charged particles, charged currents, electric charges had better be able to do things to electric and magnetic fields. So that's the topic for tonight. But as always in this course, the basic question is whether the laws of physics, and in this case the laws of the electric and magnetic field, are the same in all reference frames. That's the thing we've been concentrating on in the study of relativity, is the idea that the basic laws of physics are the same in all reference frames. Now, one of the things, we're going to write down Maxwell's equations in a moment, but one of the basic things that we learned by, well, let me go back a step. One of the basic questions has to do with light. All of relativity theory had to do with light. If Maxwell's equations are the theory of light, and Maxwell's equations tell you that light moves with the speed of light, and Maxwell equations are the same in every reference frame, it stands to reason that light will move with the speed of light in every reference frame. This was precisely the puzzle that Einstein wrestled with so hard. How is it possible to get a description of nature in which light moves with the same velocity in every frame of reference? The thing which ensures that is that the laws of physics are the same in every reference frame. And in past lectures, we saw that what that meant is that the equations of physics should be expressed in terms of quantities which have definite transformation laws when you go from frame to frame. That means scalars that don't change. It means vectors, 4 vectors, it means tensors, and it means all the things that we discussed last time when we discussed the transformation properties of the various things in physics. Let me just remind you what this equation looks like if it's expressed in a covariant form, in a form which is the same in every reference frame. It looks like an expression involving not electric and magnetic fields, well, yes, electric and magnetic fields, but a tensor, a field tensor. And I'll remind you in a little while what that field tensor is, but it's an antisymmetric field tensor which is built up out of the electric and magnetic fields, and it's multiplied by the 4 vector of velocity. This is the muth component of the force. The muth component of the force is written in terms of a 4x4 antisymmetric tensor, whose transformation properties we know, and the 4 vector of velocity. In this form, the Lorentz force law is written in a form which is manifestly the same in every reference frame. So that's our goal, is to write all of the laws of physics, in particular the Maxwell equations today, in a form which is the same in every reference frame, which means writing it in terms of vectors and tensors and so forth. Now, let's just talk for a little bit before we get into it deeply. Let's talk about the kind of effects that charges have on electric and magnetic fields. Not that electric and magnetic fields have on charges, but that charges have on electric and magnetic fields. Well, first of all, we know that if we have an electric charge, we'll call an electric charge Q. Q stands for the electric charge. If we have an electric charge of a certain magnitude, it creates around it an electric field. You've all seen pictures of this. The electric field spreads out away from the charge, very much like a fluid emanating from a pipe might spread out, except it spreads out in 3 dimensions. That's the electric field created by a point charge. Another example is if we have an electric current moving through a wire, and electric currents are nothing but moving electric charges. Electric charges moving through a wire, those electric charges, their motion creates a magnetic field. And the magnetic field is a field which circulates around the wire, like that. So these are examples of how charges and currents create fields. What happens, for example, if you move the charge? Supposing I suddenly move the charge from one point to another point. Then the field has to rearrange itself. Instead of pointing out of this point, it will still point out of this point. But it can't do that instantly. Why not? Because somebody out here is not allowed to see an effect before light could have been transmitted to this point. So the field cannot suddenly rearrange when you move a charge. It rearranges by spreading out a wave of rearrangement, so that a little bit after the charge has been moved, nearby the charge, the field has been rearranged, but far away, it's just as it was before. And then as time goes on, a wave spreads out away from the charge that signals the field far away to rearrange to accommodate the fact that the charge has moved. If you move the charge back and forth, what will spread out is an electromagnetic wave. If you vibrate the charge back and forth, then what you will see going out is an electric and magnetic wave that spreads out just like a light wave, in fact. That's what an antenna does. An antenna simply moves charge back and forth like that. The same thing is true of currents in wires. If you suddenly reverse the current in a wire, you would reverse the sign of the magnetic field. Instead of the magnetic field circulating around this way, the magnetic field would circulate around in the other direction. But that signal can't get very far in too short a time. Einstein's rule was no signal ever gets faster than the speed of light. So it takes some time for somebody far away to discover that the current has been reversed. That means that the magnetic the change in the magnetic field, the fact that it's changed direction, spreads out in a wave, and again, that's an electromagnetic wave. And if you oscillate the charge back and forth, if you oscillate the current back and forth, you send out an electromagnetic wave. That's the basic physics that we want to describe by Maxwell's equations. Before we do, I want to do a little bit of review from last time. First, I just want to remind you about wave equations. Equations describing fields, in this case describing fields that can produce waves. The first example, and we talked about it last time, was a scalar field. A field that doesn't have any indices mu and nu, but is just a single number at each point in space. Each point in space, there's a quantity, the field phi. It depends on x and t. And it can vibrate, it can shake, it can do all sorts of things. It can form wave fields. The last time we discussed the kind of equation, the kind of wave equation that governs such fields, and I'll just remind you. Remember what d mu is. D mu stands for the derivative with respect to the four directions of space-time, x and t. Mu runs over four values, x, y, z, and t. Incidentally, remember that x here really stands for x, y, and z. Perhaps I shouldn't call it x. I'll call it x. Well, let's continue to call it x. But it really stands for the four components of space, and also t stands for the time. D by d mu means the derivative with respect to any one of these. So that's an ordinary derivative. And we can differentiate phi. A simple wave equation, a very simple wave equation, would just say that the derivative of a field is 0. That's not a very interesting wave equation, and the reason is what it says is the field is absolutely constant. If all of its derivatives, the x and the y and the z and the time derivative are 0, that means the field doesn't change at all with anything, and so that's a very boring wave equation, completely boring. A less boring equation we get if we differentiate it again. I'm now using notation that we described last time, or several times in the past, where an upper index and a lower index differ only by the sign of the time component. So that this would really mean the second derivative with respect to time of the field minus the second derivative with respect to x squared minus the second derivative with respect to y squared minus the second derivative with respect to z squared is equal to 0. Notice, as usual, because I'm lazy, I've set the speed of light, c, equal to 1. You can go home and, as an exercise, figure out where the speeds of light go into this equation. All right, let's imagine now a wave moving down the z-axis. A wave moving down the z-axis. It's moving down the z-axis, and that means phi only depends on z. It doesn't depend on x and y. It may also depend on time. If a wave is moving and you're standing still watching it, of course you're going to watch it go up and down, so it will depend on time, and it will also depend on z where you are, but it won't depend on the other directions. So a wave moving down the z-axis, we can completely ignore these two terms, which are the derivatives of phi in the direction in which it doesn't change. So this is not there. And our wave equation for a wave moving along z, along the z-axis, sorry, this should be z, shouldn't it? Should equal 0. What kind of solutions does such an equation have? We talked about it last time, and there are two basic solutions that this equation has. One of them is a function of z plus t, and the other is a function of z minus t. These are the two solutions which represent waves moving to the right along the z-axis and waves moving to the left. This one represents waves moving to the right along the positive z-axis. This one represents waves moving along the left, to the left. What function? Any function. Any function, any shaped wave profile, take any shaped wave profile at all, and allow it to just move uniformly along the z direction. That constitutes a wave moving down the z-axis along the positive z direction. That's a function of z minus t. If the wave moves in the other direction, then it's the same function of z plus t. So that's the basic facts that we learned last time about waves. And there's one particular special kind of wave, the sine or cosine wave. Let's just write it down for future reference. A wave which really has a wavy look to it, like this. Well, you can guess that's either a sine or a cosine. And so, for example, a wave of this type moving off to the right would be a solution of the wave equation which has the form cosine of z minus t. Z minus t because it's moving to the right. And furthermore, you can throw in a constant here, usually called k, the wave number. Any constant. The bigger the constant is, incidentally, the shorter the wavelength of the wave. So if k is big, the wave looks like this. If k is small, the wave looks like this. Those are the basic facts that I want you to remember about wave equations, and in particular wave solutions, that they are functions of z minus t, z plus t. They can have different wavelengths, and they can be sines, cosines, and they move to the right or they move to the left. That's it. That's what we need to know about waves. Before we go ahead with Maxwell's equations, just to remind you, since it's been a week since we went through this, I will remind you of a little bit of mathematics, elementary mathematics. First of all is the notion of the cross product of two vectors. If we have any two vectors, these are ordinary vectors, not four vectors now, ordinary three-dimensional vectors in three-dimensional space, then we have the cross product, B cross A, the cross product of two vectors. The cross product is itself another vector. If we have two vectors, each pointing in some direction with a given length, we can multiply them together and make another vector. The cross product is defined by its components. So for example, the x component of B cross A is defined. This is definition is defined to be by times ax minus bx times ay. And now if you want to find the other components, you just cycle through x, y, and z. So for example, B cross A, the y component, you go x to y equals B, well, y goes to z, x goes to y. The root is x to y to z, z back to x. B goes to z, y goes to z, x goes to y, minus b, y, x goes to y, a goes to z. And likewise for the last, I'm doing this once, I won't do it again. B cross A, z component of it is equal to x, y, the next, y, z, the next one must be x, bx, x, y, the next one must be z, minus bz, ax. These are definitions. These are definitions of the cross product between two vectors. Notice that the cross product itself has components. And so it must be a vector. Okay? Now, another way of multiplying two vectors together is the dot product. The dot product of two vectors is a scalar, A dot B, and it only has one component. It's the same in every reference frame, or same when you rotate the reference frame. And its definition is AX BX plus AY BY plus AZ BZ. Can that be read? I hope that can be read. AX BX plus AY BY plus AZ BZ. That's the dot product, and it's a scalar. That's one set of concepts that we've been through several times. Now the other set of concepts are the curl of a vector and the divergence of a vector. And here's the way you think about them. They're built up out of derivatives of the components of the vector, partial derivatives with respect to x, y, and z. All you have to imagine in your head is that derivative with respect to x, and derivative with respect to y, and derivative with respect to z, pretend that those symbols are the three components of a vector. They're not. They're the three components of a derivative. But just pretend that they're the three components of a vector. And now imagine del cross a vector A. What does that mean? It's something that's made up out of the derivatives of the components of A, but, oh, I'm sorry, the three components are called the vector del. Del is just a shorthand for upside down triangle. Del cross A. How do you make it? Well, you just go back to this formula, and wherever you saw A, stick in either d by dx, d by dy, or d by dz. So the curl of A is then just given by, well, we have A, so that's d by dx. I should have called this B, shouldn't I? It would have made more sense and been nicer if I would have called this B. All right, so instead of A, we write the three components of the derivative. Wherever we see B, we just stick B. So that's Bx slow down. We're doing the curl. The curl is over here. The x component of the curl, del cross B, the x component of it. All right, that's this. All right. So it's ax by, well, that's d by dx by minus d by dy bx. We can go through it and cycle through it and find the other components of the curl of B, but they're always made up d by dy, d by dy. They're always made up of derivatives of the components of B in the same pattern, in the same exact pattern that the cross product is made up. What about del dot B? That's called the divergence of B. Del dot B, well, we come to the definition of the divergence of the dot product. Ax times bx, that will be d by dx bx plus d by dy by plus d by dz bz. Now, these two objects, they're composed out of derivatives of the components of vectors. If a vector is constant in space, if it's a vector field which is constant in space, it has neither a divergence nor a curl. Roughly speaking, a vector has a divergence when it seems to be emanating. A vector field has a divergence when it seems to be emanating out of some place, like this. A vector has a curl when it seems to curl around some place. So if we had a magnetic field, for example, in a wire that was going into the blackboard, that vector would have a curl. If we have an electric charge giving rise to an electric field pointing out from some point, that field would have a divergence. We've gone through these things before. These are not new, just reminding you of them. And now I want to write down Maxwell's equations in terms of these objects. Our goal is going to be to write Maxwell's equations. That's easy. You can get them off somebody's t-shirt, lots and lots of t-shirts with Maxwell's equations on them. But then to understand in what sense they are the same in every reference frame. That's our goal, to see that Maxwell's equations can be written in a form which is the same in every reference frame. All right, so let me write them down. Curl of the electric field. You have the electric field, you construct its curl, is equal to minus the time derivative of the magnetic field. That's Maxwell equation number 1. Maxwell equation number 2, divergence of the magnetic field is equal to 0. All that says is that the magnetic field doesn't have any sources in the same sense that the electric field does. It doesn't emanate out from a point. It tends to wind around things. Okay, the next equation is an equation similar to this, but it involves del cross of the magnetic field, and it's equal to plus dE by dt. So these two equations look very similar. It's almost as though you interchanged electric and magnetic field, but not quite. There's a sign difference between them. If you just interchange the magnetic and electric field, you get the wrong sign here. And the last one is just del dot E equals 0. In quite parallel with the magnetic field here. These are the basic Maxwell's equations, but these are the Maxwell's equations when there are no charges around, in the absence of charges and currents. Let me put back in what happens when there are charges and currents. In other words, these are the equations that are called the vacuum Maxwell equations. They describe electric and magnetic fields in completely empty space with no electric charges, no currents. Let me just tell you now what happens if you add in some electric charges, some electric currents, and so forth. They do have an effect on things. And so, for example, I'm going to write in red here the actual thing that goes. The charge density is called rho, and it's the amount of electric charge per unit volume. At every point in space, there may or may not be some charge. In every little cell of space, there may be some charge. The charge per unit volume is called the charge density. So what really goes here is the charge density. But if there is no charge density, well, then it just isn't there. Over here, there's another term, and it's the electric current. It's called J, and I'll define it for you later. But for the moment, I want to study the Maxwell equations without electric current and charges. We want to see if we can understand why those equations are the same in every reference frame. How can that possibly be? Why is it a puzzle? It's a puzzle because, as we're going to see, these equations describe light waves moving always with the same speed. They always move with the same speed, the speed of light. They move down the axis with the speed of light. How can they possibly be the same in every reference frame? After all, if I was a reference frame moving down following the wave, I would expect to see it moving slower. Nevertheless, these equations are the same in every reference frame, and in every reference frame they say the speed of light is exactly the same. So let's see if we can recast these four equations in a form which is the same in every reference frame. We have the tools to do it. What we have to remember is that the electric and magnetic fields combine together, we did this last time, combine together into a tensor, into an antisymmetric tensor. So let's remind ourselves of that. There's an antisymmetric tensor, F mu nu, and it's made up, it's 4 by 4, it's a matrix, and its components are made up out of the electric and magnetic field. Since it's antisymmetric, it has zeros on the diagonal. Incidentally, in the first row in the first column, I'm going to put the time component, the x, y, and z components. All right, we don't need this here. All right, so let me just fill it in for you. Minus the x component of the electric field, minus the y component of the electric field, and minus the z component of the electric field. And down here, we have plus E sub x, plus E sub y, and plus E sub z. An antisymmetric matrix always has the property that what's above the diagonal here is the negative of what's below the diagonal. All right, now what about in these missing slots over here? That's where the magnetic fields go. Right over here, you have minus B sub z, B sub y, and minus B sub x. And then down here, you just have the reflected plus B sub z, minus B sub y, and plus B sub x. This is the electromagnetic field tensor. Right. It transforms under Lorentz transformations as an antisymmetric tensor. I showed you how to do that last time, and there's nothing new about it for the moment. Let's see, we would call this component over here the Tx component. The first row here refers to time. The second row, well, the first row is time, the second row is x, the third row is y, the fourth row is z, and likewise for the columns. We would call this E, or we would call this F, this element over here would be mu equals T, nu equals x. Okay? So as mu and nu both run over x, y, z, and t, we fill out this matrix. That's the notion of the electromagnetic field tensor. And as I said, it transforms in the right way to be a tensor. There is another tensor that you can make up out of the electromagnetic field. It is also a tensor, and it is made up by simply replacing electric field by magnetic field and magnetic field by electric field. We just look at these equations and we see that the electric field and magnetic field occur almost symmetrically. It might not be a great surprise that there's another tensor which is made up of exactly, I won't write equal, but another tensor. It's usually called F with a little twiddle on top of it. And all it is it's the same object except with electric and magnetic fields interchanged but not quite. You don't quite change electric to magnetic and magnetic to electric. You change electric to magnetic, but magnetic to minus electric. Do I have that right? No, I don't quite. You replace electric by minus magnetic and magnetic by electric. That's in order to account for the sign difference here. When you do that, you discover that there's another tensor quantity. I'm not going to try to prove for you that this transforms like a tensor. It's just a straightforward exercise. And I'm not as young as I used to be, so I don't do as much exercise as I used to on the blackboard. I won't do it, but we'll just write it down. Wherever you see electric, put minus magnetic. Wherever you see magnetic, put electric. So F twiddle, the other electromagnetic field tensor, again, 0 on the diagonals, and then plus b sub x, b sub y, and b sub z. And then wherever we see magnetic, we put back electric. So minus Ez, Ey, minus Ex. And then on the other side here, you just have to remember that it's antisymmetric. So everything on the reflected side of the matrix here is just the opposite, the negative of what it is in the upper half of the matrix. I won't bother writing it out. These are two tensor quantities, both of which have the same transformation properties, and under Lorentz transformations form a coherent set of objects which are a tensor, antisymmetric tensor. If we can succeed in writing Maxwell's equations, here they are right here, if we can succeed in rewriting them in terms of these objects in a way that looks covariant, which looks the same in all reference frames, then we will have proved that these wave equations here, that these equations are the same in every reference frame. This is not hard to do. So let's see if we can guess the answer. Notice that Maxwell's equations each have one derivative in them. They don't have second derivatives. They have many derivatives, of course. There's a derivative with respect to t, there's derivatives with respect to x, but they never have higher derivatives. They never have second derivatives, third derivatives, fourth derivatives, and so forth. And so we might try to see if these equations here can be rewritten in terms of these field tensors. What can we write? We have F mu nu. That's the electric and magnetic field. We can differentiate it. But what can we differentiate it with respect to? We can differentiate it, of course, with respect to some x. But we want to make this equation, whatever it is, we want to make it the same in every reference frame. And that means we want to match indices, covariant and contravariant indices. About the only thing we can write down is this. Derivative with respect to x mu of f mu nu is equal to 0. First of all, let's count how many equations there are here. Let's count how many equations there are. There's one for each nu. Remember, we sum over mu. Mu is a summation index. All right? So that's not a free index in this problem. There's one equation for each nu. That means there are 4 equations. Those 4 equations we will see are, let's see, they are these 4 equations right here. Why do I say there are 4 equations here? Here's 1, and now there are 3 components of this vector equation. This is a vector equation. There are 3 components, Ex, Ey, and Ez. 3 components here, 1 here. Those are 4 components. Let's check. Let's actually check that these 4 equations are what we get from this. It's not hard. We just write it out. First of all, mu can be t, d by dt, of ft nu, plus, in fact, let's specialize. Let's take nu to be z, just for fun. Let's take it to be z and see what we get. D by dt of ftz plus d by dx of fxz plus d by dy of fyz plus d by dz of fzz equals 0. That's what this would say if it's true. Okay. What about this term? Derivative with respect to z of fzz. Fzz is 0 because all of the diagonal elements are 0. All right, so we can forget this. This isn't there. Fzz is 0. And what is fxz? Well, to see what fxz is, we go to the x row and the z column. That's by. So let's just plug it in. That's by. What is fyz? For that, we go to the y row to the zth column, and that's minus b sub x. So that gives us minus b sub x. Well, that's looking good. This is d by dx of by minus d by dy of bx. This looks very much like a piece of the curl of b. And that's what it is. What about ftz? Well, we go to the t row, to the zth place, and we get minus e sub z. So this is minus the derivative of e sub z with respect to t. All of that equals 0. Well, if you look at it carefully, you'll see that it's exactly the equation over here, the zth component of it. The time derivative of e sub z is the z component of the curl of b. That's exactly what we have here. So we check that the, let's see, which component was that? That was the z component over here. The z component just gives us back one of the Maxwell equations, namely the z component of a Maxwell equation. The only other case which is interesting is to write down the time component here, or the t component, t for time. Well, let's continue to call it mu nu. Let's work out the time component of this equation. What does this read now? First of all, it has a term which is d by dt of ftt. That's mu equals t. But that's 0. ftt, that's right here. That's 0. So that's 0. And then we have, what else? D by dx of fxt plus d by dy of fyt plus d by dz of fzt. Well, what is fxt, yt, and zt? Those are just the components of the electric field. fxt, minus with a minus sign, is e sub x, the other one is e sub y, and the other one is e sub z. So all this says, when packaged neatly, is that the derivative with respect to x of ex plus the derivative with respect to y of ey plus the derivative with respect to z of ez is equal to 0. That, my friends, is just del dot E equals 0. For the moment, we've been ignoring charges and current density, charges and currents. So you can see that four of the Maxwell equations, 4 of the 8 Maxwell equations, just have the form of a relativistically covariant, same in every reference frame, vector equation. It's a vector equation because the left-hand side is a vector. It's a vector because it is the derivative where you've contracted the index mu. There's only one index left over, and so this is a vector equation. It's the same in every reference frame. The point is that if you went through the entire labor of doing the Lorentz transformations on the coordinates and on the components of E and B, you would find out that after the Lorentz transformation, the equation was exactly the same. Okay. What about the other half of the Maxwell equations? Well, those have exactly the same form, except with twiddle here. Of course they have exactly the same form. F twiddle is the same as F, except with E and B interchanged, and an extra minus sign thrown in. Well, that's exactly what's here. If you go from here to here by interchanging electric and magnetic fields with an extra sign here, the equations are the same. So this is a powerful way to rewrite Maxwell's equations, again, without charges, without current densities. This is a powerful way to rewrite them in a simple and elegant form, but it's not the simplicity and elegance which is important. It's the recognition that these are four-vector equations and therefore the same in every reference frame. So Maxwell's equations then are relativistically invariant. They don't change from frame to frame. We'll put back charges and currents in a little while, but, or maybe next time. Well, no, I think we'll do it this time. But now that we've found that Maxwell's equations are the same in every reference frame, what do they say? What are the implications of these 8 equations? What kind of electromagnetic fields do they allow? What do they describe? So let's again forget currents and densities for the moment. 0, nothing there. And let's study these 4, they're not 4 equations, they're 8 equations. Let's study them and see if we can make wave equations out of them. Now if we go back, I don't know what we did with the wave equation, we had it someplace here. There it is. The wave equation is an equation with second derivatives. Second derivatives mean you differentiate twice. Okay? Maxwell's equations all have only first derivatives, but they have 2 distinct fields, E and B. We're going to find out that having, these are called first order equations because they only have first derivatives, but we have first order derivatives, first order equations for E and first order equations for B, 2 variables. We're going to find out that that's equivalent to having second order equations for either the electric field or the magnetic field separately. This is not hard to do. This is easy to do, so we need, let's see, we'll need a clear blackboard over here, and we'll need to manipulate this a little bit. I have E and B all mixed up, but I want to write an equation just for the electric field. I want to try to isolate just the electric field and see how it behaves. So here's what I do. Let's see. Take this equation over here, and let's differentiate it with respect to time. It's got only one time derivative in it. Let's differentiate it again with respect to time so that we get a second time derivative. Then it will be d second E by dt squared, second derivative of the electric field, and that's going to equal del cross the time derivative of B. If I differentiate with respect to time over here, I just get the second time derivative of the electric field. If I differentiate with respect to t over here, that just differentiates the magnetic field with respect to time. Okay, that hasn't helped yet. I still have the electric and the magnetic field in the same equation. The goal was to get rid of the magnetic field. But look, right here I have the magnetic field, or its time derivative, written in terms of the electric field. So I can be clever and simply get rid of dB dt here and call it curl of E, minus the curl of E. Okay, so let's just, let's first, it was, what was it? It was del cross dB dt. And now for dB dt, we substitute minus curl of E. So that gives us a minus sign and a curl of E. Here we have an equation which only involves the electric field, second derivative with respect to t on the left-hand side and various complicated derivatives on the right-hand side. What I'm going to do is I'm going to take the x component of this equation, Both sides of the equations are vectors. E is a vector. Differentiating it with respect to time leaves it a vector. And the cross product, or the curl of a curl, is also a vector. So let's take the x component of both sides. The x component of both sides. What we have to calculate is the x component of the curl of the curl. That's a slightly tedious operation. If you like, you can go to sleep for 2 minutes until I get the answer, but I will do it on the blackboard for you. Okay, del cross E, the x component. Right. What we have to know is that the x component of a curl, the x component of a curl is equal to the derivative of the z component with respect to y minus the derivative of the y component with respect to z. All right, we are taking the x component of del cross A, That's this. All right, so now we want the x component of del cross E. That means I just substitute for A. Wherever I see A, I substitute del cross E. So let's see, what's that going to give me? That's going to give me d by dy of AZ, which should be del cross E, the z component of it, minus d by dz of del cross E, the y component of it. But now we substitute for these components the same trick. And here is the result, the grand result. It's d by dy with derivative of EY with respect to x minus derivative of EX with respect to y. That's d by dy of this term. And then there are two more, plus d by dz of dEx by dz minus dEz by dx. And then I think that's it. That's it. Two terms. Okay. Okay, wake up now. The worst is over. Let's see what we have. We're calculating the x component of a vector. We're calculating the x component of a vector. Let's see what we have here. We first of all have second derivatives of Ex with respect to y. Now let's see what we have here. First of all, d by dy squared of Ex. That's this term. Let me cross them out as we pick them off. That's this. D by dy squared, two derivatives with respect to y of Ex. We have two derivatives with respect to z of Ex, plus second derivative with respect to z squared of Ex. That's this. And then we get two other terms which look a little mysterious. What are they? They are derivative with respect to x of dy Ey. That's this term over here. It looks a little different because I've interchanged the x and y derivative. All right, it was derivative with respect to x followed by derivative with respect to y. You're allowed to interchange those. So the first term here is d by dx of dy Ey. And then there's another term which is d by dx of, I think it's dz Ez. Neither one of these, the top one or the bottom one, looks very elegant. But if I add a term to the top and subtract the same term from the bottom, the whole thing will have a nice form. So let's add plus d by dx squared Ex, And let's now subtract d by dx of d by dx ex. I have added and subtracted exactly the same thing. Now you should be able to see a pattern. First of all, we have dy ey plus dz ez. This should be I think overall sign mistake. Yeah. dy ey, dz ez, and dx ex appear inside here. What is that? That's just del dot E. But del dot E is equal to 0. That's one of Maxwell's equations. And so all of this, dx ex plus dy ey plus dz ez is just 0. Not there at all. What about this term? This is nice. The second derivative with respect to y squared, x squared, and z squared of the same quantity, e sub x. Let's put it together now. Let's put it together. What was it? Here's what we were doing. The second derivative with respect to x of t squared is minus del cross e, the x component of it. And that's exactly what we computed over here. That long, tedious computation just give us a left-hand side. Let's erase it, and let's replace it by what we computed. And you'll see a pattern. It is d by dx squared ex plus d by dy squared ex plus d by dz squared ex. If you've kept track, which you probably have not, of the original wave equation, you'll see that this is just a wave equation for the component Ex. Ex is a field which satisfies just the same old wave equation that we wrote down for phi. If you remember, we wrote down a wave equation for phi. It had exactly the same form. And so E, the electric field itself, satisfies a wave equation. The good old wave equation, the same wave equation which had right-moving and left-moving solutions which could be sines and cosines. What have we learned? We've learned that there are waves of electric field that can propagate. We've learned that the wave equation, which gives rise to propagating waves that can move to the left or right, applies, or any other direction, of course, but which applies to the scalar field, also applies directly to the components of the electric field. All right, let's see whether we can build ourselves an electric wave, an electromagnetic wave. This equation has solutions of the form, for example, Ex is equal to cosine of, let's just take a simple example, z minus t. This would be a wave moving down the axis. It's the wave equation. It has a solution, which is a wave moving down the z-axis. All right, that's what this cosine z minus t is. I could put a constant k, but let's leave it out. It only complicates things. All right. This would be a wave whose electric field is pointed along the x-axis. Let's draw some coordinates. Here's z, here's x, and here's y sticking out of the blackboard. This is a wave moving down the z-axis. Its electric field is along the x-axis. For simplicity, let's take it not to have any component along the y-axis, and it looks like a cosine. So it's an electric field, points up, points down, points up, points down, and it propagates, needless to say, with the speed of light. Why the speed of light? We've worked in units in which the speed of light is 1. And this is just a wave moving down the z-axis with unit velocity. z proportional to t, the whole thing just makes an excursion down the z-axis without changing shape. All right? That's the electric field. And I've chosen it arbitrarily to point in the x direction. Incidentally, a wave, an electromagnetic wave, where the electric field points along the x direction is called a polarized wave, polarized along the x-axis. This is polarized light. Polarized light, polarized along the x-axis. Okay? What about the magnetic field? Can the magnetic field be any, oh, wait, before we do that, we've decided arbitrarily somewhat to set the y component equal to 0. Let's just do that. We could have put a y component in also, but I decided just to keep it simple. What about the z component of the electric field? Let me prove to you that that has to be 0. It has to be 0 because del dot E is equal to 0. What is del dot E? It's the derivative of the x component with respect to x, but the x component doesn't depend on x, plus the derivative of the y component with respect to y, also doesn't depend on y, plus the derivative of the z component with respect to z. These two terms in the divergence of the electric field vanish, so must this one. So what that says is that the derivative of Ez with respect to z must be equal to 0. In other words, the z component of the magnetic field, of the electric field, cannot vary as you move along here. It must be constant. Constant could be a constant electric field. Let's just throw it away. A constant electric field is not very interesting. It's certainly not part of a wave motion. We could get rid of it by putting it between capacitor plates and canceling the uniform electric field. The point is that the wave part of the field, the part that varies as you go down the z-axis, must not be there for the z component. So only the x component of the electric field is there. The y component and the z component are just not there. 0. What does that mean about the magnetic field? Well, we can use this equation over here to tell us something about the magnetic field. First of all, what about the curl of the electric field? The curl of the electric field, what components does the curl of the electric field have? Well, the only components that it can have would have to come from something like dEx by dz. That's the kind of thing that appears in the curl of the electric field. Well, we would also have minus dEz by dx. This would be the y component of the curl, but the z component isn't there. We've already established that, so that's not there. So, for example, this would be the y component of the curl of the electric field. It's there. If you differentiate Ex with respect to z, you'll get an answer. You will get an answer. So there is a y component to the curl of E, and that's all. There is no other component to the curl of E except for the y component. We could look for some other component. Let's look for the z component. That would be dx by y minus dy, dey by x. Well, Ex doesn't depend on y, and Ey is 0 altogether. There's no other component. So the only component of the curl of E is along the y-axis. The electric field is along the x-axis, is the z-axis, and the magnetic field is along the y-axis. Why is the magnetic field along the y-axis? Because its time derivative is along the y-axis. If the time derivative is along the y-axis, the field itself must be along the y-axis. So we see then that the magnetic field, let's draw the magnetic field in green, lies perpendicular. Let's see if we can draw it. Here's the magnetic field. Here's the electric field. Electric and magnetic field are perpendicular to each other, and they're also perpendicular to the motion of the wave. That's what follows from these equations. The whole set of equations has wave-like solutions with the electric and magnetic field both oscillating, they're both going up and down, except the magnetic field is going left and right, and the whole thing is proceeding down the z-axis. That's the nature of electromagnetic waves. Electric and magnetic fields perpendicular to the direction of motion, all moving uniformly down the axis with the speed of light. What's more, you can be sure that if you were to take this electromagnetic wave and look at it from another frame of reference, it would have exactly the same properties. Why? Because the Maxwell equations are the same in every reference frame. So the properties of electromagnetic waves will be the same in every reference frame, and they'll always have this property of moving with the speed of light and having crossed electric and magnetic fields perpendicular to each other and to the direction of motion. That's the character of light and all other electromagnetic radiation. All right, now let's put back the things we took out. Namely, let's ask what happens when we have charges and currents in Maxwell's equations. How do we describe it? How do we describe it, and what does it do? Most important, is it Lorentz invariant? In other words, is it the same in every reference frame? That is our major goal, to show that the laws of electromagnetism are the same in every reference frame. So what do we have to do? I'll just remind you that the two Maxwell equations on the right-hand side, strictly speaking the four Maxwell equations on the right-hand side, get modified. They get modified by putting a charge density, and I will explain what that means on the right-hand side over here, plus a current density. The current is the current of electric charge. So let me explain what those things mean. The charge density, which is called rho, this is the symbol rho. I don't know why charge density has always had the symbol rho associated with it, nor do I know why the current has the symbol J associated with it, but it goes way back. I think it goes back to Faraday, but if not, it goes back further than me anyway. Rho, the charge density, is defined in the following way. Imagine you have lots and lots and lots of electrons, and they could be other kinds of charged particles, protons, even some neutral particles, it doesn't matter, but that space is filled with a lot of particles. So many of them, charges of different kinds, that you're tempted to think of it as a continuous distribution of charge. The charge, just like water is a bunch of molecules, but when you look at water in a coarse-grained way, you think about water as being a nice continuous distribution of stuff. Okay. Now, you take a little volume of space. A little volume of space, let's call it volume V. Make it a small volume. We're going to think calculus, we're going to think differentially. A small volume of space, let's call it dV, and take the charge in that small volume of space. If the volume of the space is very small and shrunk to smaller and smaller dimensions, of course the charge will also shrink to smaller and smaller dimensions. But the ratio, let's call the amount of charge in there, let's call it dQ, a small charge in a small volume, and the ratio of the amount of charge per unit volume is called the density. Okay. So it's the charge per unit volume, except at each point of space evaluated separately. So it could vary from place to place. You can have regions with heavy charge density, regions with light charge density. And in calculating this, you add up the plus charges, you subtract off the minus charges, all the obvious things, add the protons, subtract the electrons, and get a net charge density in each region of space. And that charge density is itself a function of position, but it could also depend on time. How could it depend on time? Well, for example, charges could move from one place to another. This whole pile of charge could move over to here, in which case, if we stood at a particular point, the charge density would change. It would change from something to nothing. So the charge density also depends on the time. Okay. Now, it can't depend in any old way. There is a rule in nature, and it's called the conservation of charge. The total amount of charge in the world must not change. Right? So what is the total amount of charge in the whole world? You add up all of the charges in each little cell of space. You add it all up, and that becomes an integral. The total charge, let's call it capital Q, total charge in the world is the integral over all of volume of space of the charge density. Little dv here, that just means you add up all of the cells. In each cell, there's a charge which is equal to dq, which is rho times dv. So you add up all the rho times dv's. That's what an integral is. It just means add them all up. And that gives you the total charge, in this case, in the whole world. We could also, for example, just talk about the charge in a region of space. We could pick a particular region of space with well-defined boundaries, this room, or some other particular region of space, and talk about the charge in that region, in which case this integral wouldn't go over all space. It would just go over the selected region, in this case, for example, the room. And that would be the charge inside the room. Now, charge is not allowed to just change someplace and reappear someplace else. It's not allowed, according to the laws of physics, for reasons that will become more or less clear in a second, to suddenly disappear over here and reappear over here. Well, let's go back a step. First of all, the rule of nature, and it's an empirical law of nature, the empirical law of nature is that the total amount of charge in the universe never changes. Okay? That's called conservation of electric charge. But the rule is stronger than that. For example, you could have a situation where charge on the Earth disappears, and instantly, with nothing happening in between, the same charge appears on Mars. That would satisfy the rules of the conservation of charge, that the amount of charge doesn't change. What was lost on Earth reappeared on Mars, and the conservation of charge does not tell you that something has to happen in between. But that's forbidden. That's not the way charges change, and that's not the way charges move. They can't disappear over here and reappear over here unless there's a flow of charge in between. In other words, if charge disappears over here and reappears over here, somebody in between had better be seeing a current flow between them. How do we express this idea that charges don't just appear and disappear, and in fact they don't move from one place to another except by virtue of a current of electric charge flowing from one place to another? So for that, we have to invent the idea of a current. So let me explain what a current is. It's a simple idea. Let's put this upstairs. Bring this downstairs. Let's take a little area in space. There's a little area in space. I'm going to redraw it. A little area, a small area, an infinitesimally small area. It's normally called d sigma. D indicating that it's small, differential, and sigma standing for surface area. Okay? So the amount of surface area is called d sigma. But when people write d sigma, they mean something a little more. They mean a vector. Now, how the hell can an area be a vector? Well, what you do is you take that area and you assign to it a vector perpendicular to the area element. We'll decide in a few minutes which direction. Do I do it to the left or do I do it to the right? But for the moment, just imagine assigning to every little element of area a vector whose length, whose magnitude is the little area and whose direction is perpendicular to the direction of area. That's called the surface element vector, the surface element vector d sigma. I could put a little vector symbol above it, but we don't need it, just d sigma. Now, we can ask how much charge flows through that area in a unit of time. Right? How much charge flows through that area per unit time? Or better yet, we can ask how much charge per time per unit area flows through there. The charge flowing through there will certainly be proportional to the area. If the area is tiny, a small amount of charge will be able to flow through it for a given situation. If the area is made large, a larger amount of charge can be flowing through it. The charge per unit area, per unit time, charge per unit area, let's write the words. Charge per unit area per unit time through a little surface element is called the current. Now, the current is a vector. The current is a vector. You can see why that should be so. Current is kind of like flow. Right? Think of it as a flow of all the electrons and protons flowing through space. At any point, the flow has a direction, namely the direction that the charges are flowing in, and it also has a magnitude, and the magnitude is the charge per unit area per unit time flowing through that area. That's the definition of the current, and as I said, it is a vector. If I want to know the amount of charge per unit time flowing through the surface element, then what I do is I take the dot product of the surface element with the current, both of them being vectors. If, for example, the current is flowing parallel to the surface, that means the current is perpendicular to d sigma, then this product is 0. So if the current flows along the surface, no current flows from one side to the other. Okay? If the current is flowing perpendicular to the surface, that means it's parallel to d sigma, then you get the full maximum brunt of the flow through the surface element. That's why it's the dot product. The dot product measures the component of one vector in the direction of the other. So this measures the component of the flow in the direction perpendicular to the surface element. And it is not the charge per unit area per unit time, but just the charge per unit time. This is the charge per unit time, charge per unit time through the surface element d sigma. So now you have the idea of the flow of charge and the sometimes called the flux of charge. Flow or flux of charge and current or electric current are all the same thing. Okay? Notice we're not necessarily talking about a current through a wire. A current through a wire is a special case, and if we opened up the wire and made it a little bit big, we could put little surface elements of area in there and see that the current through a wire is made up out of exactly these kind of currents, fluxes of charge through the wire. But that's a special case. We can have currents flowing through space, space currents, currents flowing along sheets, or just currents flowing along three-dimensional space. And that's the definition of J. Okay, now let's concentrate on the following question. Here we have a region of space. It has some charge in it, and the charge in it is the integral over the volume of the charge density. If there are currents flowing, there may be currents flowing into or out of the region. Let's choose to make up the boundary of the region out of a whole bunch of little surface elements. All right, so the boundary is made up, I mean the boundary. If we thought of this as a balloon, then the rubber of the balloon we would make up out of a lot of little surface elements here. And now let's, by definition, point their little d sigmas out of the balloon. Let's choose to make them out of the balloon. Supposing there's a net current flowing out of the balloon, what does that say about the charge inside the balloon? Incidentally, I'm not imagining the balloon changing its size or anything. It's just a fixed region of space. If there's current flowing, net current flowing out of the surface, then the current on the inside must be changing. Okay? The only way that the current can change, the only way the charge can change on the inside, is by passing from the inside to the outside. So if the charge is changing, if the charge on the inside is changing, you can be certain that there must be a flow of current through the boundary, and that tells you that there must be a J. In fact, we can write down a simple equation. We can write down that the time rate of change of the charge inside this region, the q by dt, that's equal to the integral dv of d rho by dt. The time rate of change of the electric charge inside this region must equal the current that's passing out through the boundary, actually with the opposite sign. If current is passing out through the boundary with a positive sign, then the charge must be decreasing on the inside. So it must have a minus sign in this formula. And what's the total charge that passes out of this region per unit time? The total charge passing out of the region per unit time is just the integral of the current dotted into the surface element. We just add up all the currents passing through each one of these surface elements. That's the integral here. And this is a theorem now, or if you like, perhaps it's a law of nature rather than a theorem, that the time rate of change of the current on the inside is equal to the flux of charge passing out through the surface of the balloon. And that's given by the integral of the current dotted into d sigma. Okay. Now we need a true theorem, a mathematical theorem rather than a law of nature. And the mathematical theorem, which we won't prove, it's called Gauss's law. Sorry, it is not called Gauss's law. It is called Gauss's theorem. Look up Gauss's theorem. It's sometimes called the divergence theorem. But I will tell you what it is. It's a relationship between, this is called a surface integral. It's an integral of a vector quantity over a surface, over a bounding surface. It can be related to an integral over the interior. And here's the theorem, called Gauss's theorem. Gauss theorem. It says that the integral of any vector integrated over the surface is equal, now this is an integral over the surface call it surface, is equal to an integral over the volume. Now, if I had my class here, I would ask them what goes in there. Anybody know? No, okay. The divergence of the vector. The divergence of the vector itself. So it's a relationship between a surface integral of a vector and the integral over the volume of the divergence of the vector. It's not obvious. I'm not going to prove it. It actually doesn't take very many lines to prove, but let's assume it. If we assume it, then we can write the right-hand side of this equation as an integral over the volume. So it's an integral over the volume another integral over the volume of the divergence of the current. It's the spreading out of the current. The spreading out of the current, you know what it's like? It's almost like this. I'll give you a picture of what the divergence of a vector is. If you thought of the vector as the flow vector of some water, perhaps flow vector of some water, right? And supposing some water was being pumped in at each point of space, some hidden little pipes that you can't see are bringing water in from outside and dumping it in. The pipes end in different places in space, so the water is diverging out away from the tips of the pipes and going out and filling up space. The divergence of the water, or the divergence of the flow of the water, is basically just the water coming out of these individual pipes. And what this theorem says is that the amount of water that's coming out of these little pipes that are ending at this point and flowing out, where's that water going to go? It has to go out of the surface. It has to go out of the surface, and that's this expression here, that the divergence, the integral over the boundary of the surface flow is also equal to the integral over the interior of the volume of the divergence of the vector. So that's a general theorem about vectors. It doesn't have anything particular to do with electricity. It doesn't have anything particular to do with anything special other than the mathematical properties of vectors. All right, so now we have a new theorem that the integral over any volume, take any volume whatever, the integral over any volume of the time rate of change of the density of charge is the integral over the volume of the divergence of the current. If two integrals like this are equal, but they're equal not only for some particular volume, but it's true for every volume that you can think of, then there's only one way that that can be true. If for any region that you can pick, the integral over the volume of one thing is equal to the integral over the volume of another thing, the only way that that can be true is for the things themselves to be equal. That again is a mathematical theorem, but it's more or less obvious that if for any region the integral of one quantity is equal to the integral of another quantity, the two quantities have to be equal. And we come to an interesting conclusion about the connection between charge density and current. It says that the derivative with respect to time of the charge density, that's this, plus, I'm bringing everything over to the left-hand side, the divergence of the current, let's write that out. That's derivative with respect to x of j sub x plus derivative with respect to y of j sub y plus derivative with respect to z of j sub z equals 0. Now, if this is to be true in every frame of reference, and I didn't specify anything particular about any particular frame of reference when I told you this little story, if it's to be true in every frame of reference, it better have the form of some invariant equation. And it's not hard to imagine how you make an invariant equation out of this. You first of all say that the current, well, not first of all, you say that the current Jx, Jy, and Jz, together with rho, four quantities, rho, Jx, let me put the x upstairs now, Jy, Jz, form a four vector. They form the four vector J mu, where mu goes from time and the three components of space. That is what is suggested by having these four components, rho, Jx, Jy, and Jz. And then this equation, which is called the continuity equation, it's called the continuity equation, it takes the simple form that d mu j mu is equal to 0. What does that say? It says derivative with respect to t of jt plus derivative with respect to x of jx, blah, 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 is equal to 0, which is exactly what this says. So the way to make this continuity equation be an equation that's true in every frame of reference is to think of the four components of current and density as a four vector. That's not too surprising. The current kind of represents the velocity of the motion of the charges. As we've seen over and over again, the velocity vector is a four vector. The velocity vector of an object, the relativistic velocity vector of an object, is a four vector. And so it's not so surprising that the flow of a fluid should also be described by a four vector, and the four vector is the four vector of current and density. Well, okay, now we have an object, the four vector of current and velocity, that we can try to put into Maxwell's equations somehow. Let's go back to Maxwell's equations, which seem to have disappeared off the blackboard. So I guess, well, let's see if they have. Maybe they're underneath here. Nah. Okay, so let's write Maxwell's equations again. This time, putting in the charges and currents. Okay, here they go. Del dot E is equal to rho. Del dot B is equal to 0. Del cross E is equal to minus dB by dt. These are all vector equations, and del cross B is equal to dE by dt plus J, where J is exactly the same J that I defined here, the current per unit area per unit time. Okay. What I assert, and which we'll check, is that these equations are exactly the same as the following equations. d mu, f mu nu. Remember what f mu nu is? F mu nu is a 4x4 antisymmetric matrix, a tensor, which is built up out of the electric and magnetic field components. All right? That is equal to J nu. Notice the left-hand side, you've contracted the mu index, so the mu index is not really a real index here. It just has one nu index, on the right hand, the nu index. Okay, let's check that this simple covariant equation, this is clearly a covariant equation. This is a tensor. Differentiating a tensor gives you a vector. This is a vector. And so this equation would be invariant and the same in every reference frame, assuming that J transforms as a vector. So let's just check that we get the same equation. I'm not going to do them. Let's see. The ones that's relevant here are the ones with the right-hand side, the ones with current and charge density. There are four equations here for nu, for the four different values of nu. There are four equations here. 1, 2, 3, 4. So let's check to see if any of them are the same. First of all, let's take the time component. The time component would be d mu f mu t is equal to jt. But what is jt? That's the time component of the of the 4-vector of current. It's rho. So on the right-hand side, we have rho. And what about the left-hand side? To see what the left-hand side is, we have to go and rewrite the field tensor, but we don't need the whole thing. All we really need to remember is, let's see, that that we have the components of the electric field 0, Ex, Ey, and Ez along here. We also have minus Ex, minus Ey, minus Ez, and then we have the magnetic field sitting in here in various ways. Okay, so let's see what we have. We have only the time components of F. That means the components along this first row here. We can write this as dx fxt plus dy fyt plus dz fzt. Am I missing one? Yes, I'm missing one. I'm missing dt ftt. But ftt is 0. All the diagonal elements of the matrix are 0. So this is 0. Now what is fxt, fyt, and fzt? Those are the components of the electric field. So what is this? This is just dxex plus dyey plus dzez. In other words, it is del dot E. The left-hand side is just del dot E, and the right-hand side is rho. We could go through the other components. In other words, exactly the same thing. Instead of taking the time component here, we could take space component, for example, and set this equal to jx, and we would discover the x component of this equation. So the upshot of it is that the connection between charges and fields, the way in which charges and currents, electric charges, electric currents, the way they generate fields is Lorentz invariant. It's the same in all reference frames. On the other hand, we've already seen that the way that the fields influence the charges as forces on them are also the same in all reference frames. So we see that basically all of the equations of electromagnetism can be written in a form in which we can immediately check that they're tensor equations and therefore the same in every reference frame. That was the real goal of this, to show that the laws of electromagnetism are the same in every reference frame, number one. And number two, to demonstrate that the laws of electromagnetism lead to light waves moving with the speed of light. From those two things, it follows that light travels with the speed of light in every frame of reference. And that sort of closes up and finishes up the task started by Einstein of rewriting all the laws of physics in a way which is the same in every frame of reference.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.